All right, ready to dive into some serious number crunching. Today we're tackling regression and time series analysis.
Yep, two big topics, but hey, we're here to make sure you feel confident, ready to ace those exam questions.
That's the goal. So first up, multiple regression. It sounds intense.
Well, it's like taking linear regression to the next level. Instead of one factor, we're looking at how multiple variables impact something else. Like, imagine you're trying to figure out what drives stock prices.
Okay, yeah, that's complex. Lots of things could be at play.
Right. It's not just the overall market. Company size matters. So does their valuation. Multiple regression helps us untangle all those influences.
So we can actually see, like, how MUCH each factor contributes.
Exactly. We get these numbers called slope coefficients. Each one tells you how much, say, a stock price is expected to change when a factor, like market performance, moves up or down.
So it's like building a model that says, hey, if the market jumps 1%, we expect this to happen to the stock price.
That's the idea. But hold on, before we get too excited, we got to make sure our data is playing by the rules. Multiple regression has some assumptions.
Assumptions. Sound a bit like a trust exercise.
Kinda. Think of it as a checklist. First, we want linearity. We're hoping our data follows a straight line relationship. If it's all over the place, we might need a different approach.
So it's like hoping our real-world data actually looks like those neat graphs from algebra class.
Exactly. Then there's homoscedasticity, big word, but basically it means we want our prediction errors to be kind of consistent across the data. If they're wildly different, that's a red flag.
The prediction errors. So we're admitting our model won't be perfect,
Yeah.
but we want those imperfections to be, predictable.
Right. We also want those errors to be independent, like flipping a fair coin. Each flip shouldn't be influenced by the one before it.
Okay, no loaded dice allowed in our data analysis. What else are we checking for?
Normality. We're assuming our errors follow a normal distribution, that bell curve shape. If they don't, it might mean our model is missing some key ingredients.
Like a sign that we need to dig deeper, find those missing variables.
Exactly. And lastly, independence of independent variables. We don't want our predictor variables to be too cozy with each other. It makes it hard to tease out their individual effects.
So it's like building a team of experts. We want each one to bring something unique to the table.
That's the perfect analogy. Now, to check these assumptions, we have tools like scatter plots. They help us visualize relationships in our data and spot potential issues.
Scatter plots.
Yeah.
Yeah, those rings a bell. Lots of dots on a graph.
You got it. And one particularly cool type is a pairs plot. It's like seeing all the relationships between your variables at once helps you spot any strange connections.
Pairs plot. Haven't heard of that one. Sounds handy. So let's say we've built our model, checked the assumptions. How do we know if it's actually good?
Excellent question. That's where goodness of fit comes in. We're basically asking, how well does our model explain the variation in our dependent variable?
Like, is it just a coincidence or are we capturing something real?
Exactly. And one of the key tools for this is R-squared. It gives us a sense of how much of that variation our model explains.
So a higher R-squared is better. Like closer to 100% means our model is super accurate.
That's the general idea. But in the real world, you rarely get a perfect R-squared.
Okay, so it's more like aiming for a high score, knowing perfection is hard to achieve. But what if we've got lots of independent variables? Does R-squared still work?
It does, but there's a twist. We often use adjusted R-squared in multiple regression.
Why adjust it? Isn't a high R-squared always good?
Here's the thing. Adding more variables can artificially inflate R-squared, even if those variables aren't really helping much. Adjusted R-squared takes that into account.
So it's like a reality check, making sure we're not just adding variables for the sake of it.
Exactly. It rewards us for being efficient, choosing the variables that truly matter. Now, there are other measures like AIC and BIC too. These are more about balancing how well our model fits with how complex it is.
It's like we're trying to strike a balance between explaining the data and keeping our model as simple as possible.
You got it. Now, let's imagine we want to check if a bunch of variables together are really doing their job. Like, are they all contributing to the model?
Like a group project. Are they all pulling their weight or is some slacking off?
Perfect analogy. That's where the joint F-test comes in. It helps us test multiple coefficients at once to see if they're statistically significant as a group.
So we're looking at the team performance, not just individual stats.
Precisely. Now let's talk about those data points that just seem off. The ones that don't quite fit the pattern.
Oh yeah, the outliers. They can really mess things up, right?
They can. That's why we do influence analysis. It helps us identify those data points that are having an outsized impact on our results.
So we're looking for those rebels, the data points that are breaking the rules.
Exactly. Visualization helps, but we also have more precise tools like leverage and studentized residuals. These help us spot those data points that are pulling our model in the wrong direction.
So it's not just about throwing out outliers, it's about understanding why they're different and what they might be telling us.
Exactly. Now, what about data that's not numerical, like gender or location? Can regression handle that?
Yeah, that's a good question. It's not like you can plug male or female into an equation.
Right. That's where dummy variables come in. They transform categories into something our model can understand. Think of it like a secret code.
So we're turning categories into numbers, like 1 for urban, 0 for rural.
You got it. And by looking at the coefficients for those dummy variables, we can see how each category impacts the outcome.
So it's like comparing apples to apples, even though our data isn't all numbers to begin with.
Precisely. Now, what if we want to predict a probability instead of a specific value, like the chance of a customer clicking on an ad?
That's different. Probabilities aren't just numbers on a scale, are they?
That's where logistic regression comes in. It's designed to handle situations where we want to predict a yes or no, a success or failure. It gives us probabilities neatly between 0% and 100%.
So it's like putting guardrails on our model, making sure the predictions make sense.
Exactly. And those coefficients in logistic regression, they tell us how each variable nudges that probability up or down.
Okay, so it's still about understanding those relationships,
Yeah,
but with a different type of outcome in mind.
you got it. We also use different tests, like the likelihood ratio test, to see how well our logistic regression model is doing.
Okay, my head is spinning a bit with all these regression types.
It's a lot to take in, but remember, focus on the core ideas and how they connect. You're doing great.
Thanks. Now, are we ready to tackle time series analysis? It sounds almost futuristic, analyzing data across time.
It does have a sci-fi vibe, but really, time series analysis is just about understanding data that's collected over time. Think stock prices, weather patterns, even the spread of diseases. It's everywhere.
So instead of a snapshot, we're looking at a movie, seeing how things change.
Exactly. And that's where it gets really interesting. Let's start with trend models. They help us understand the general direction of the data over time.
Trend models. So are we talking about, like, is something increasing or decreasing? Like if ice cream sales go up every summer, that's a trend.
Yep, that would be a seasonal trend, actually. But you're right, trends can be linear, going up or down at a steady rate, or even exponential, where the changes accelerate over time.
So we're not just looking at whether it's going up or down, but how it's going up or down.
Exactly. We have different trend models to capture those different patterns. But here's a tricky thing about time series. It often breaks one of the key assumptions of regression.
Wait, which one? The no loaded dice rule.
Close. It's about the independence of errors. In time series, today's value is often influenced by yesterday's value, so our errors might be correlated.
Ah, so our errors aren't just random. They might have a pattern, too.
Right. That's where the Durbin-Watson statistic comes in. It tests for this correlation, which we call serial correlation. It's like a warning sign.
So if that statistic is flashing red, we need to rethink our approach.
Yep. We might need a fancier model, like an autoregressive model. These models use past values of a variable to predict future values.
So it's like the data has a memory, and we're using that to make predictions.
Exactly. Think about predicting tomorrow's temperature. Wouldn't you want to consider today's temperature, maybe even yesterday's?
Okay, that makes sense. But how far back in time should we go? Do we need data from a year ago?
That's a great question. It leads to the concept of lags. In an autoregressive model, we decide how many past values or lags to include.
So more lags mean we're looking further back in time.
You got it. But there's a catch. These autoregressive models work best when the time series is covariance stationary. That basically means it's not too wild, its properties are fairly consistent over time.
Okay, so covariance stationary is like a prerequisite for using these models. But what about those times when the future truly is unpredictable?
Ah, you're thinking about random walks. It's a type of time series where the value in one period is essentially the previous value plus a random shock.
So it's like flipping a coin. You never know what you're going to get next.
Exactly. Stock prices are often modeled as random walks, but don't worry, even random walks can be analyzed just with a bit more care.
So it's like we might not be able to predict the exact value, but we can still understand how it behaves.
That's the spirit. And to check if we're dealing with a random walk, we have a test called the Dickey-Fuller test. It helps us detect those unpredictable wanderers.
Okay, so it's like a way to confirm our suspicions. But even if it is a random walk, We're not totally out of luck.
Not at all. Sometimes we can transform it into a covariant stationary series using a technique called first differencing. We focus on the changes rather than the absolute values.
So it's like smoothing out the randomness, making it more manageable.
Exactly. Now, let's switch gears a bit and talk about moving averages. You might have heard of them in finance for smoothing out stock prices on a chart.
Oh, yeah, I've seen those. They create those smoother lines, right?
Yeah. Right. But moving averages can also be used to build time series models. They're called, unsurprisingly, moving average models, or MA models.
So we're taking that smoothing concept and turning it into a prediction tool.
Precisely. And in MA models, we use past forecast errors to predict future values. It's like learning from our mistakes.
Okay, so we're saying, hey, we were off by this much last time. Let's adjust our aim.
Exactly. Now we have AR models using past values, MA models using past errors, and even ARMA models that combine both.
Wow, it's a whole family of time series models. I'm starting to see how they all fit together.
You're getting it. And we'll dive into more of these intricate relationships in the next part of our deep dive. Get ready because time series, they can get wild.
I'm all for a wild data ride, but my brain's still processing all those ARMA, ARMA models. It's a lot.
It is. But just like with any family, each model has its strengths, right? Which one you pick depends on your data, what you're trying to figure out.
So it's like choosing the right tool, right? You wouldn't use a screwdriver to hammer a nail.
Exactly. Now buckle up because we're adding another layer. Seasonality.
Seasonality. Yeah, that makes sense.
Right.
Like stores selling more during the holidays, ice cream in summer. It's everywhere. But how do we actually catch that in our models?
Well, one way is with those lags we talked about. We can add seasonal lags to our model.
Seasonal lags. So like if we're looking at monthly sales, we'd include what happened 12 months ago to capture that yearly pattern.
Exactly. It's like giving our model a memory boost, reminding it what usually happens this time of year. But how do we know if seasonality is even an issue? Do we just eyeball it on a graph, look for those peaks and dips?
That's what I was thinking. Just look for those obvious ups and downs.
Visualization is a good start, but we can also use those autocorrelations. Remember those?
Yeah, those are pretty handy.
Right. If we see strong autocorrelations at those seasonal lags, like 12 for monthly data, that's a sign.
A sign that seasonality is playing a role. We better pay attention.
Exactly. And then we can use a seasonal RMA model. It's like the all-in-one tool. Handles the regular AR, MA stuff, PLUS, the seasonal swings.
Sounds powerful. But with all this complexity, are there, like, common mistakes people make? Things to watch out for?
Oh, for sure. One biggie is overfitting. It's when your model gets too focused on the specific data you gave it.
So it's like memorizing the answers instead of understanding the concepts, acing that one specific test, but then blanking on everything else.
That's a great analogy. Overfitting means your model might not work well on new data.
So it's like a tailor making a suit that fits perfectly in the store, but then you move and it's all wrong.
Exactly. We want a model that captures the real patterns, not just random noise. And to avoid overfitting, we use techniques like cross-validation. It's like giving your model a practice test.
A practice test before the real deal, see how it performs in the wild.
Exactly. We split the data, train the model on one part, then test it on another. If it does well in the test, we're more confident it's actually learning, not just memorizing.
Okay, overfitting? Check. Any other common traps?
Another one is forgetting about context. We can't just blindly apply models. We need to understand what's going on in the real world, the factors driving the data.
So it's like, if we're looking at, say, housing prices, we need to think about interest rates, the economy, not just the numbers themselves.
Right. It's about being a data detective, not just a data cruncher.
Speaking of detective work, let's talk about ARCH for a second. Autoregressive conditional heteroscedasticity. That's a mouthful.
I know, right? But basically, ARCH is about understanding how the volatility of those errors we talked about, how much they're jumping around, can change over time.
So it's like the errors themselves are having their own little roller coaster ride.
Exactly. And if we ignore that, our models might not be as reliable. Luckily, we have tests to check for ARCH, and if we find it, we can use techniques to adjust for it, make our models more robust.
Okay, so ARCH, that's something else to watch out for. Now, what about those times when we're looking at multiple time series, not just one? Like trying to see if they're connected somehow.
Ah, now you're venturing into multiple time series analysis. It's a whole other world with its own challenges. One thing to be careful of is spurious regressions.
Spurious regressions. Sounds a bit like a fake magic trick.
Kind of. It's when we find a statistically significant relationship between two time series, but they're not actually related. It's like seeing shapes in the clouds.
So we might think we've discovered something, but it's just an illusion.
Exactly. This often happens when both time series or random walks, those unpredictable ones. We might see a high R squared, but the relationship is meaningless. It's a mirage.
Okay, so we need to be careful about jumping to conclusions, especially when dealing with multiple time series.
Right. But there are also cases where two time series that look like random walks actually are connected. It's called cointegration. It's like two ships sailing on the same ocean. They're both being tossed around by the waves, but they're still on a similar path.
So it's like a genuine connection, even though each series might look random on its own.
You got it. And we have a test for that too, the Ingle-Granger-Dickey-Fuller test. It's like a relationship test for time series.
Okay, so it's like, are you really connected, or are you just fooling yourselves?
Exactly. If the test says they're cointegrated, then we can be more confident that the relationship is real, not just a coincidence.
Well, multiple time series, that's a whole other level. But I'm starting to see how all these pieces fit together, from basic trends to random walks to those intricate relationships between different series.
It's like a giant puzzle, isn't it? And with each piece we put in place, we get a clearer picture of how data unfolds over time.
Speaking of the bigger picture, let's talk about interpreting these models. It's one thing to get the numbers, but what do they actually tell us? How do we make sense of those coefficients and p-values in the real world?
That's the key, right? It's not enough to just do the math. We got to understand what it means. So for example, that coefficient on a lagged value in an AR model, if it's significant, it tells us that the past is influencing the present.
It's like that saying, history repeats itself. But in this case, it's the data repeating itself.
Exactly. And the bigger that coefficient, the stronger that influence from the past.
Okay, that makes sense.
Yeah.
Now, what about the intercept? Does that still mean the same thing in a time series model?
Not always. In regular regression, the intercept is often like a starting point. But in time series, especially with trends or those random walks, it might not have that clear meaning.
So we shouldn't read too much into it.
Right, especially if it's not statistically significant. Now, before we wrap up this section, a word of caution. We've talked about the power of time series analysis, but it has limitations too.
Limitations? Like what?
Well, one big one is that we're using the past to predict the future. But as we all know, the future doesn't always follow the script. Things change.
So our models are based on this assumption that the patterns will continue, but that's not always guaranteed.
Exactly. We got to be humble, know that our models are only as good as the data we feed them and the assumptions we make.
Assumptions, right. It's all built on that foundation.
It is. Now, one last brain teaser. We talked about understanding the context of our data, those real-world factors that might be at play, but how do we actually blend that qualitative stuff with our quantitative models? They seem like different universes.
Yeah, it's like trying to mix oil and water. How do we bridge that gap?
It can be tough. Sometimes we use dummy variables for categories, like you mentioned before. Other times, it's about using our knowledge of the situation to adjust the model.
So it's like combining art and science, using the tools in ADR judgment.
Exactly. Data analysis isn't just about the numbers, it's about the story behind the numbers.
Well said. We've covered a ton of ground, from basic regression to the complexities of time series. I'm exhausted, but in a good way.
Me too. It's been a great journey.
Before we move on, any last nuggets of wisdom for our listeners? Key things to remember.
I think the most important thing is that time series analysis, it's a process. It's about exploring, trying things out, refining our models as we learn more.
It's like detective work, gathering clues, testing theories, getting closer to the truth with each step.
I like that. And just like a good detective, we got to be skeptical, question our assumptions, and always be on the lookout for those pitfalls.
Pitfalls, yes. We've talked about a few, like multicollinearity, outliers, spurious regressions. Any others lurking in the shadows?
Well, one that often trips people up is overfitting.
Overfitting. That sounds familiar. Didn't we talk about that earlier?
We did. It's such a common problem that it's worth repeating. It's when our model fits the data we use to build it perfectly, but then it fails miserably when we try to use it on new data.
So it's like a student who crams for a test and gets a perfect score, but then can't remember anything the next day.
Exactly. We don't want a model that just memorizes the data. We want a model that actually understands the underlying patterns.
So how do we avoid overfitting? Is it just a matter of using fewer variables in our model?
It can help. But it's not just about the number of variables, it's also about the complexity of the model. We can overfit with a simple model if we're not careful.
So it's like Goldilocks and the Three Bears. We don't want a model that's too simple, too complex, but just right.
Exactly. We want a model that captures the signal in the data without getting bogged down in the noise.
So how do we find that sweet spot? Is there a magic formula?
There's no magic formula, unfortunately. But there are techniques like cross-validation that can help us find a good balance. It involves splitting our data into training and testing sets, building the model on the training set, and then seeing how well it performs on the testing set, the data it hasn't seen before.
So it's like giving our model a trial run, seeing how well it generalizes to new situations.
Exactly. And if it does well on the testing set, we can be more confident that it's not overfitting.
Okay, overfitting? Check. What other modeling mistakes should we be on the lookout for?
Another common one is neglecting the context.
Context, what do you mean by that?
I mean, the real-world factors that might be influencing the data. We can't just blindly apply models without understanding the big picture. For example, if we're modeling retail sales, we need to think about things like holidays, promotions, economic conditions, and even the weather.
So it's like being a data detective, not just a data cruncher. We need to understand the story behind the numbers.
Exactly. Data analysis is not just about applying formulas, it's about understanding the underlying dynamics and using data to gain insights.
Now, we've talked a lot about models and predictions, but ultimately, data analysis is about making decisions, right? How do we use these models to inform our choices?
That's the million-dollar question. Models are tools, and like any tool, they need to be used wisely. We need to be aware of their limitations, the uncertainty inherent in any prediction, and the potential consequences of our actions.
So it's not just about plugging in numbers and getting an answer. It's about thinking critically, weighing the risks and rewards, and making informed decisions based on the best available evidence.
Exactly. And remember, models are based on assumptions, and those assumptions might not always be valid.
So a healthy dose of skepticism is always a good thing.
Absolutely. Now, before we wrap up, I want to emphasize that data analysis is not just about numbers and algorithms, it's about people.
People. How so?
Well, data analysis is ultimately a human endeavor. It's people who collect the data, build the models, interpret the results, and make decisions based on those insights.
So it's not just about the tools, it's about the people using the tools.
Exactly. And we need to be mindful of the human element, the biases, the assumptions, and the values that shape our data analysis.
That's a great point. Data analysis is not a value-neutral activity. It's shaped by our perspectives and priorities.
Absolutely. And as data becomes increasingly central to our lives, it's important to be aware of these ethical considerations and to ensure that data is used responsibly and for the benefit of humanity.
All right, so we've covered a ton on regression, time series, even touched on some of the bigger picture stuff. My brain's full, but I kind of want more. What else is out there in the time series world?
Oh, there's always more. We talked about those ARMA models, right? But remember how sometimes data has those regular patterns A and D, the seasonal swings?
Yeah, like those ice cream sales spiking in summer.
Exactly. For that, we've got the seasonal ARIMA model. It's like the super model handling all those dynamics at once.
Seasonal ARIMA, so like the ultimate tool for complex data.
You got it. Think of it as the Swiss Army knife of time series models.
Okay, I'm seeing how these models kind of build on each other, each one getting more, I don't know, specialized.
You're right. It's not a one-size-fits-all situation. Picking the right model, it all comes down to understanding your data, knowing what you're trying to figure out.
Makes sense. Now, we've talked about building the models, but what about interpreting them? Those coefficients, p-values, they're not just numbers on a page.
Right. Absolutely. We got to translate those numbers into real-world meaning. Like, let's say you've got a significant coefficient on a lagged value in an AR model.
That means the past is influencing the present.
Right.
Like the data has a memory.
Exactly. And the larger that coefficient, the stronger that influence from the past.
Makes sense. Now, what about the intercept? Does that have the same meaning as in regular regression?
Not always. With time series, especially if you've got trends or those random walks, the intercept might not be as clear-cut.
So we should be careful about how we interpret it.
Exactly. Now, time for a reality check. We've talked about all the cool things time series can do, but it has limitations.
Limitations? Like what?
Well, we're using past data to predict the future, right? And as they say, past performance isn't always a guarantee. Things change.
So our models are making this assumption that the patterns will continue, but that's not always a sure thing.
Right. We got to be humble, you know? Our models are only as good as the data we use and the assumptions we make.
Assumptions.
Yeah.
Always the foundation.
They are. One last thought. Remember how we talked about understanding the context of the data, all those real-world factors?
Yeah, that stuff can be hard to capture in a model, right? It's like trying to mix oil and water.
It can be. Sometimes dummy variables work for categories. Other times you need to adjust the model based on your knowledge of the situation.
So it's a blend of art and science, using the tools, but also our judgment and experience.
Exactly. Data analysis, it's not just about the numbers. It's about understanding the story behind the numbers and making those informed decisions.
Well said. Think we've done a pretty good job unpacking all this today, from basic regression to those complex time series concepts, even some of the bigger picture stuff. Hopefully our listeners are feeling a bit more confident, ready to tackle their own data adventures.
Absolutely. And remember, the world of data, it's huge and constantly changing. So stay curious, keep learning, and don't be afraid to experiment.
Great advice. Thanks for joining us on this deep dive. To everyone listening, until next time, happy analyzing.